Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Anodot for sponsoring today's event. Anodot is an integral supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, and that would include Tableau, IBM, Alteryx, Teradata, Crowdflower, Exaptive, and Qubel, to name just a few. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Today's webinar with Anodot is entitled Accurate Anomaly Detection with Machine Learning. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We'll have one presenter that I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. I'm very pleased to introduce today's speaker, Ira Cohen of Anodot. Ira is a co-founder of Anodot and its chief data scientist in charge of developing and inventing its real-time multivariate anomaly detection algorithms that work with millions of time series signals. Now, prior to Anodot, he was chief data scientist at HP Software. He holds a PhD in machine learning from the University of Illinois at Urbana-Champaign and is the holder of over a dozen patents. So Ira, thanks for being with us today. We're looking forward to your presentation. Now, achieving accurate anomaly detection requires more than statistics. Simple assumptions like normal distribution don't work in the real world. Time series data, represent anything from customer acquisition to application performance to manufacturing KPIs, they tend to have many different behaviors that need to be modeled accurately. These include seasonal patterns, non-stationary behaviors, and intricate correlations between signals, amongst others. So in today's webinar, we'll discuss the fundamental machine learning techniques for anomaly detection, requirements for anomaly detection systems in various use cases, issues and pitfalls to watch out for when you're implementing anomaly detection, and some common use cases and examples. So Ira, with that, whenever you're ready, you can begin. Thank you.
Thank you, Bill, and let's start this presentation. So thanks again for hosting us. And the title of the talk is Accurate Anomaly Detection with Machine Learning. And indeed, what I'm going to talk about today is, first of all, why do you need anomaly detection? Why do companies need anomaly detection? I'll talk about some of the design principles for anomaly detection when you're building an anomaly detection system. I'll talk about some of the methods in anomaly detection that are common, especially ones for real-time, and I'll also demonstrate the Anodot system. We also, for the people on the webinar today, we actually opened up a very free taste of Anodot that requires no commitment or of any kind. And you'll see throughout the slides, the URL at the bottom of the slide lets you actually download small instructions on how to send data into Anodot without any need for login or any account. So with that, let me start and move to the next slide. So why do you need anomaly detection at all? So if we're looking at various industries, basically anomaly detection detects the things that are unknown in data, and that typically saves time and money, or both. So if we're looking at common use cases of anomaly detection in web services, it's a very common use case to detect business incidents and detect unknown business opportunities from the data. So basically, business incidents, and I'll describe a few, could be anything that if impacts your revenue or any type of incident that that could affect your system. Another area that is very hot these days is industrial IoT, where proactive maintenance is one of the main use cases, or detecting issues in factories or machines. And those also require oftentimes anomaly detection. Security is an obvious one, detecting unknown breaches or threats or attack patterns, and not just the ones that are known. And another area that is very interesting is machine learning. So we're seeing machine learning algorithms being pushed into production in many cases and many use cases. So how do you detect that your machine learning algorithms are not really behaving the way you expect them to? Anomaly detection is again a way to detect the unknowns in your machine learning algorithms. And there are many other examples. So let's talk about business incidents, because it's a very common use cases for web services, and you can transfer that to all the other domains as well. So how do you detect business incidents? It's usually driven by metrics that measure over time the performance of various aspects of the business. And these could be purchases per product if you're in e-commerce, conversion per campaign if you're an ad tech company, and those are revenue-generating metrics, metrics that measure the revenues of the business. There are business-generating metrics like leads and visitors and usage and engagements, which are measured per geography, per user segment, per page on your application, per browser of your users, per device, and so on. And you've got application performance metrics that also impact the business, like application performance or errors or usability measures. And of course, there are IT measures like infrastructure utilization, middleware utilization, network, system, and you measure those per host, per database, per switch. So all of those help you detect whether there are business incidents and how they're affecting the business, and it's all metric driven. So this is not new, and now the question is how do people do it? How do people do it today? So in a lot of cases, people detect business incidents manually, looking at dashboards, which is a common thing that a lot of people do. So you put up a few graphs and have people gaze at dashboards and then detect with their eyes that there are all sorts of strange patterns and react to them. Another way is to set static thresholds on your metrics. So that works if you know really well the range, the good range and the bad range of your metrics. But even oftentimes in those cases, you may miss all sorts of incidents that fall within the known range of good or bad, but are still maybe bad for that particular point in time of the day. So that's another manual way of detecting business incidents. But both of these ways are really not scalable. Setting thresholds on metrics when you're starting to measure millions of them is not really feasible. And then oftentimes it's not even possible. You don't know the good range from the bad range in many of these KPIs. Looking at dashboards, that's good, but it's only limited to the number of time series you can put on your dashboard, and it's also limited by the capacity of the people to gaze at the dashboards. So again, it's not scalable when you're talking about a big business with millions of metrics. So really the way to do it is to use automated anomaly detection. So have a system learn what is normal, do what people do with their eyes, and figure out automatically where there are anomalous events and highlight those and alert on those. So here are a few examples. This is a metric showing the number of visitors for a web service coming from one geography. And you can see in the orange in the middle here, or towards the end, there is a drop in the number of visitors compared to that time of day and day of week. Another example, decrease in ad conversion on Android devices for a certain campaign. Again, have the system learn the normal behavior, which is highlighted here by the shaded area around the actual line, the graph. And whenever it exceeds that or goes below it, you can alert about it as an anomaly. Of course, sometimes looking at a single metric and detecting anomalies in a single metric is not enough to understand what is going on. So here's an example of a price glitch where the top graph measures the number of purchases done for a particular product, and the bottom graph shows the revenue that is obtained from the purchases of that product. Now, in this anomaly, what we see is that the number of purchases increases dramatically, but the revenue, it increases, but it's not increasing as expected, which is indicated by the shaded area. So both are in an anomalous state, but the fact that the number of purchases went up and the revenue is not going up as fast is an indication that there is an issue. And ask anybody working in e-commerce, they'll tell you this happens a lot, where they publish accidentally a product for a much lower price than it should be, and then social network, people find that out through social networks or all sorts of websites that crawl through the web and start buying that product for a much cheaper price. So these are just a few examples that illustrate why detecting business incidents is important and why automated anomaly detection is an important tool for doing that. So let's go into what are the key design principles when you're actually building an anomaly detection system. So I'm listing here four. There are more than just four, but these are the four main ones that I believe are really important. The first one to ask yourself when you're designing an anomaly detection system is the timeliness. How fast do you need to detect an anomaly in your data? Is it real time or is it retroactive? And there are use cases for both, and it really changes what type of methods you're going to use. The second one is scale. Are you looking at hundreds of time series signals that describe your environment for detecting business incidents, or is it millions or maybe billions? And that makes a whole world of difference of what type of methods to use. The rate of change. Does my system that I'm measuring with all these metrics, does it tend to change over time and rapidly or very slowly? And again, that leads to whether I'm going to use adaptive algorithms or offline learning algorithms. The last one is conciseness. I'm measuring a lot of things about my system, and the question is, can I live with a univariate approach for detecting anomalies, so detecting anomalies at every single metric, or do I need multivariate methods? And that relates to conciseness because oftentimes when some incident happens, a lot of time series signals that I'm measuring, a lot of the metrics become anomalous. And the question is, do I want to see them together in some way, or can I live with them alerting me each one individually? So let's double-click on some of these and talk about what does it mean in terms of machine learning. So if I'm looking at timeliness, real-time versus retroactive, it's basically the difference between online learning algorithms and batch learning algorithms. So online learning algorithms have good properties and bad properties. So first, they're basically algorithms that cannot iterate over the data. I cannot go back and fix what I've learned. Every sample that comes in updates what I've learned so far, and I learn with every sample. Now, that leads to techniques that are typically more prone to false positives because I cannot go back and fix mistakes that may have been made with my learning. But it scales more easily because obviously I'm only going through my data once. And it's critical for real-time decision-making that I use these type of techniques. Now, if I have a problem where I don't need real-time decision-making, I can use batch learning algorithms. Batch learning algorithms take a whole bunch of data, 5 months worth of data or 1 month worth of the samples, and can find all the anomalies in it using batch learning techniques, and can iterate over the data over and over, and that's why they're easier to remove false positives in those cases. But they scale very poorly because you basically iterate over a lot of data all the time. You're doing it in batch. The next point is rate of change. Do I have a system that constantly changes? And here I am actually showing real examples of metrics from real systems. The one on the left is actually a real metric from a real system, where it started off with one behavior and then changes to a completely different behavior. So if your data changes over time and is constantly changing, which is typical for any web service measuring itself because the number of users keep adding or keep increasing, releasing more products, you're changing your products. So these require really adaptive learning algorithms that can handle constant change in the underlying data distribution. And this is the most common use case. However, there are use cases where changes are very slow. If I'm monitoring an industrial machine that was designed 10 years ago and hasn't changed much since, I can actually learn once with a lot of samples that I collected over time and not let it change at all. So this is good for closed systems, large machinery, airplanes, where it's known that the changes are going to be slow, if at all. The last point about the design principles is the conciseness of anomalies. So again, I'm measuring a lot of measures, a lot of metrics, a lot of time series about my business or my system, and it could be hundreds, thousands, or millions or billions, depending on the scale of the company. Now, I can choose to use univariate anomaly detection techniques, which is a lot of the techniques that are out there, or multivariate anomaly detection. So univariate anomaly detection, you basically learn the normal model for each one of your metrics, and then anomaly detection is done at the metric level. So I'm detecting anomalies for each individual metric by itself without correlating it to the others. The advantage is that it's very easy to scale. It's much easier to scale it because you're basically learning each time series by itself. But when there is an issue, it often causes an anomaly storm. You can't see really the forest from the trees because when something big happens, many of your metrics are going to be anomalous. And how do you understand what's going on? Another advantage that it has is that it's easier to use to model various types of behaviors of time series data that you might be collecting. You have a complex system, you might have all sorts of types of metrics that you collect, types of metric behaviors that you're collecting, and it's easier. And if you're modeling each one by itself, you can get an accurate model for each one much easier. The multivariate anomaly detection, however, it learns a single model for all metrics, and then it detects an anomaly that is a complete incident. So an anomaly is a combination of behaviors for all the different input signals that I put into that algorithm. Now, most of these techniques are very hard to scale because they're multivariate learning techniques. They're oftentimes hard to interpret. So the system would say, I see an anomaly, but if I need to present how the anomaly looks like to a human, it's often hard to do. And it often requires that all the metrics that you input into the algorithm have some sort of a homogeneous behavior. At least they should be, real valued as opposed to real values and discrete, and they have to have some sort of a homogeneous behavior. So if all of your measurements are more or less of the same type, then it's good to use these multivariate techniques. If they have very different types of behaviors, then it could lead to very poor results. Now, there is a hybrid approach, which is the approach actually we took at Anodot, which is going from the univariate model to a multivariate model in steps. So the first step is to learn a univariate model for each one of the time series and then combine anomalies to a single incident if all the metrics in the anomalies are related in some way. And how do you find that they're related? I'll talk about it in the next few slides. The advantage is that this method is scalable because we're learning the normal behavior of each metric by itself, and we're also only doing the hard work for anomalies in periods of anomalies. And because anomalies are rare, there's actually a lot less computation going on. Another advantage is that it allowed us to combine all sorts of types of metric behaviors and still be able to do the multivariate technique on top of that. All right, so let's switch gears and talk a little bit about anomaly detection methods. And I'm going to focus mostly on the real-time anomaly detection and mention a few of the batch learning techniques at the end of this section. So unsupervised anomaly detection, basically the first step is to model the normal behavior. That's the first step because it's unsupervised. So we have to model the normal behavior in some way. So the example in the time series you see above here, you see a time series. That's the bold line, and then the shaded area is the normal range expected for that time series at any point in time. So the first step is to get that shaded area going. So first we need to model the normal behavior of the metric using a statistical model or a probabilistic model, which is just a statistical model with priors. The next step is to devise some statistical tests to say whether any given sample is explained by the normal model. If it is explained, then it's normal. If it's not explained, then it's an anomaly, and that's step 3. So apply the test for each sample, flag it as an anomaly if it doesn't pass the test. So the orange part in the graph above is the anomaly because it's not explained by the normal model, which in this case is the shaded area. So that's a simplistic view of it. Now, is it really simple to model the normal behavior? So it's not so simple because there are a lot of different aspects to look for. First of all, what is the signal type and its distribution? And if you are collecting now millions of these time series data from a large-scale system, then you could have many different types of signal distribution and signal types. The third aspect is, does it have seasonal patterns? If I want an accurate normal behavior model, I have to take into account whether it has a seasonal pattern or not. The last part is, how do I adapt to changes in the normal behavior of my signal? And I have to put that into my techniques. So in terms of signal type and distributions, when we started Anodot, we had in mind that most signals are, like the top one on the left, smooth or stationary signals. Why? Because that's usually the way you think about signals and metrics. They're measured constantly all the time, and why should they behave in a very strange way other than stationary way? But once you start collecting data from real systems and real applications and real web services, you see all types of behaviors. And here are a few that are listed on the slide. So you have metrics that are very irregularly sampled. So it's missing data, it's missing samples, but it's not really at random. It's okay that they're missing samples. That's really the way they behave. Multimodal distributions, sparse distributions, stepwise signals, discrete signals. So if you really want to have an accurate normal behavior model, you have to look at all these signals and classify them automatically, because nobody can do it at large scale manually. Classify these signals to their type and the right distribution that fits them. Because if you don't use the right distribution, whatever you're going to do afterwards is going to be either it's going to be a poor model, either produce a lot of false positives or be useless and not detect anything. So I can tell you that the model that fits the smooth or stationary signals will not fit the multimodal signals that you see here, that you see there. Now, there's no real way without designing that classifier that classifies your signals to their different types. There's no real way to know what type of signal you're going to get. And from our experience, about 40% of the signals are stationary, and the rest fall into the other categories. So it's not like the stationary is the majority of the signals we see in the system. The second aspect is seasonal patterns. Seasonal patterns is really important to model the normal behavior of metrics. And we see that in many, many signals that we get from customers, especially when we're talking about web services that are driven by user behavior, but it's true for other services as well. So here's an example of a metric where you don't take into account the seasonal pattern, and this is the baseline you're going to get. It's basically that shaded area is pretty useless because it's covering almost all the signal. If you do take it into account in your model, then you can detect anomalies like the one you see right here on the right, which is more intricate anomaly where things go down compared to where it should have been during that point in time of the day. So this is a single seasonal pattern. Oftentimes we see multiple seasonal patterns being applied at the same time. This is an example of a seasonal pattern that I like to call amplitude modulation because in this case it's a daily and weekly seasonal pattern, but they're modulated on top of each other. They're not additive. And if you do take them into account, you can capture fine anomalies that you see right there. Drops in the number of in the value of that metric, in this case related to revenue, and you can see these drops that you wouldn't capture otherwise. Another example of a multiple seasonal patterns are additive signals. So additive signals is basically you have one signal and then another signal that is being added to it. In this case, this is a 4-hour seasonal pattern overlaid on top of a 24-hour seasonal pattern. So there you can see the spikes going up every 4 hours or so. And if you take those into account, you can detect anomalies like the one you see in the middle, where there should have been an increase during that period, but it actually stayed flat and even went down afterwards. That is the real anomaly. That would be very hard to capture if you didn't take into account the fact that it has multiple. So what are some techniques for detecting seasonality automatically? Because again, if you're building an anomaly detection system, an automated one, you have to detect whether there is a seasonal pattern or not in your data. Because you don't know what is the seasonal pattern. It could be 2 hours, 24 hours, 7 days, 5 hours, 17 hours. There are many seasons that will be there in your data. So these are 3 common techniques: Fourier transform of the signals, and then finding the maximums in the Fourier transform. The issue there is that it's challenging to detect low-frequency seasons. It's challenging to discover multiple seasons, and it's very sensitive to missing data. The advantage of it is that it's fast. Another technique, which is computationally expensive, is finding maximums in the autocorrelation function. And now that's a pretty accurate detection method for a single season. It's a bit challenging for multi-season, not impossible, but a bit challenging. The disadvantage that it has if you're building a large-scale system is that it's very computationally expensive. Another nice aspect to it is that it's fairly robust to gaps in the data, missing data. The last one is to do an exhaustive search. So create a cost function that defines that basically gives you a match whether there is a seasonal pattern or not, and then go through and compute that cost function exhaustively over a lot of possibilities of your season. That is very computationally expensive, but very robust to gaps, and again, challenging to discover multi-seasons. We designed an algorithm called the Vivaldi algorithm, and it's basically based on the autocorrelation function. But it's a fast autocorrelation function approach. Just to give you a sense, it's as fast as Fourier transform in terms of computation. The way we do it is by doing smart sampling of the autocorrelation coefficients, so not computing all the coefficients, but only the ones we need. And then using filter banks for detection of multiple season patterns. And this technique actually scales, in our case, to millions and hundreds of, above 100 million metrics already for the Anodot system. Some of the pitfalls of using adaptive algorithms, and I mentioned when we are doing real-time decision-making, you need to use online algorithms, and because most services change rapidly, you need adaptive algorithms. And most adaptive algorithms have some update rate. So how fast do you adapt to changes in the time series? And here are some pitfalls to the adaptive rates. So if you set your adaptive rates to be very slow, then you're going to get something that is a baseline that is not very good. You're going to get the normal range that is very, very high band around your data. If you make it too fast, then you're going to adapt where every coming sample, you might miss a lot of anomalies. So what you really need is some mechanism that will let you auto-tune the adaptive rate of every algorithm for every metric. And if you look at some of the techniques that are out there, for example, ARIMA models, you can auto-tune with Kalman filters. And of course, the question is how do you do it efficiently, because a lot of these techniques are very, very computationally expensive. Another pitfall is how fast to adapt to anomalies. So usually when you learn online with these adaptive algorithms, there is an inherent assumption that all the samples are normal, but we know that's not true. Some of the samples are abnormal. So how do you actually adapt when you have abnormal samples? So this relates to a story. So last month I attended an event called Burning Man, and it's a very, very strange event in the middle of the desert in Nevada. And when you go there, you start seeing things like this. You start seeing people riding on bicycles that look like camels, and that's an anomaly. You start seeing people on the next day, people with all sorts of weird art, and you see cars blowing fires and looking like octopuses. So those are all anomalies. But then after the fourth day, when you see people like this, it starts looking, okay, this starts looking normal. Is it really an anomaly or not? And after 7 days, when you see somebody riding a bicycle like this, you think it's normal. And then on the 8th day, when you go back to your real world and to your real job, everything else looks like an anomaly. So what's the point of this story? How fast do I adapt to anomalies? Because if I adapt as usual, and that's the first strategy. Basically, let the next sample adapt as usual. I'm going to miss most of the anomaly, and I might even screw up what happens next. So really, the strategy that should be taken is to adapt the learning rate when there are anomalies. So if you discover an anomaly, you cannot adapt as though there is nothing going on. You have to slow down or even stop how you learn. And the nice thing about a lot of the online algorithms and adaptive algorithms is that they have a learning rate that is controllable, and you can change those to make sure you capture all the anomaly and you don't adapt to it too fast. So here are some examples of anomaly detection methods and techniques, like Holt-Winters, which is a statistical method, ARIMA and Kalman filtering, hidden Markov models, and so on. And I'll leave these slides will be available so you can go through them and read their classification as well. The last point I wanted to talk about in respect to anomaly detection and large-scale anomaly detection system is anomaly conciseness. So everything I talked so far was at the single metric level. But we know that if we're measuring millions of metrics and it's a large-scale system that I am measuring, then when something happens, there are going to be a lot of metrics that are anomalous, and how do I see the forest from the tree? So the approach, as I mentioned, we have taken is that we detect anomalies at a single metric level, but then we combine them based on similarity of their behaviors. So how do you do that, and how do you do that at scale? So really our approach has been to look at 3 different types of inputs, automatic inputs that we have from the metrics, and combine them into a metric relationship graphs. So the 3 types of inputs are, do they tend to behave similarly during normal times when there are no anomalies? Do they tend to be anomalous together at abnormal times, or have some overlap in anomalies? Because that may indicate that they are related. And because a lot of these metrics have names to them, is there any similarity to the names? They describe what they're measuring, the geography, where they're being measured, the products that they're measuring, and so on. So some of the techniques that we've been using for doing this, for abnormal base similarity, we use a variation of latent Dirichlet allocation algorithm. For normal behavior similarity, obviously linear correlation is not a good fit here. So we use nonlinear similarity to compress the time series using stacked autoencoders, and for name similarity, term-based similarities from the speech literature. And now, how do you do it at scale? Well, here we employ locality-sensitive hashing at a lot of levels of the algorithm to make sure that everything scales to millions of metrics. All right, so I'd like to show you a very brief demo of the Anodot system. So I'm going to push my screen to you, so it might take a few seconds for you to actually see it. And basically, the demo is just to show you how one anomaly looks on our system, and how do people actually use it to see to actually determine that there is an incident and to investigate an incident. So here's an alert, actually a demo alert that our system produced. In this case, it arrived in email. And what you see here, that the alert is that there is an anomaly in cart conversion rate. And the idea here, I'm an e-commerce site. I'm measuring cart conversion per product and per geography, and measuring also revenue per product and geography. And I want to be alerted as an analyst in that company. I want to be alerted if there is an anomaly in revenue or cart conversion. And the anomaly here shows two metrics. The revenue metric for product category 4 in the US that dropped compared to where it should have been. So this is the end of the week, and it should have started increasing, but it didn't increase. And the cart conversion also decreased abnormally compared to that time of day. And once I see that, I want to understand why. Why does this happen? Are there other anomalies in other metrics that I don't necessarily care to be alerted on and woken up at 3 a.m. for, but could help me identify why this happened? So when I go into the Anodot system, it actually shows me all the correlated time series, all the correlated metrics to the two that I got in the alert. So this is the revenue and the cart conversion, and I can see the drop here. But at the same time, I can see that there are other metrics, in this case 3 metrics, related to the same product category, but related to product ID number 2, where I see checkout errors, increase in checkout errors, increase in checkout latency, and increase in checkout retries. So these are more technical metrics that help me figure out, okay, there is a problem with product 2 in the US, something related to the checkout. And in most of these cases, it could be something in the database, could be something in the application, but it isolates the problem really quickly for me, so I know as an analyst to send it to my IT to let them deal with it. So let's go back to the presentation. So in the last few minutes that we have before we go to the Q&A, I wanted to briefly describe or at high level describe the anomaly detection system, that architecture that we have built at Anodot, and which I think is something that you need to build similarly if you want a really large-scale anomaly detection system. So the first part is sending data into the system. Now, in the middle here, you see a component called Anodot D. That's the Anodot daemon. This is where most of the learning, the adaptive online learning, happens for each individual metric. Now, notice that it happens before the data gets stored in any type of persistent storage. And there is a reason for that. To be scalable and to be highly scalable to millions of metrics, you must work on the samples as they flow into this system. If we store them and then try to pull them out later for anomaly detection, we would need such a large database system and such a fast database system that is fast for reads and for writes that it would have been non-economical to build that kind of system. So we've built this cluster in the middle, which basically does all of the learning and the anomaly detection at the metric level as the data flows into the system and gets aggregated. And only after that process is done, we store it into the backend storage. In our case, we use Cassandra. Any anomalies get detected go into a Kafka queue, and then the grouping, the multivariate anomaly detection, the grouping of the anomalies together based on their relationships that is discovered is done in another cluster. And the reason that the Kafka queue and the anomaly grouping works well is because it only works on anomalies and doesn't work on all the raw data. And anomalies are a lot less than the raw data. It's a lot more rare. It's a rare event, so it doesn't have to be as large. On the right here, you see some offline learning algorithms, and some of the things you can run offline. For example, detecting that there is a seasonal pattern in a metric does not have to run in real time. You can run that once a day or once every 2 days on the history of the metric. Again, learning that there is a relationship between two metrics or clustering the metrics can be done in offline. And all of these jobs we run every day on all the metrics that are sent into our system. These are some numbers from a while ago. 5.4 billion daily samples are what we handle today in our system with 105 million metrics. Each metric has 2 models living in memory with it. One for modeling the normal behavior. We have another model for modeling abnormal behavior. And a lot of correlation links, 500 million. These are updated daily. 14 million of the 105 are actually seasonal models, again, updated daily. And 30 types of learning algorithms for metric classification, seasonality detection, trend, baseline models, and so on. So this is just to give you a sense of the architecture and how we handle large-scale anomaly detection. As I promised in the beginning, we are opening up, we opened up for the next few weeks for the participants of this webinar, a taste of Anodot. Basically, the single metric anomaly detection, so not the multivariate, not the correlation one, that would be more complex to open up, but a single metric anomaly detection where you can actually throw against our system time series metrics that you have. You get back immediately the results, and there are instructions to how to do it. It doesn't require login. We just ask you to register, to put in your details, and then you can download the instructions on how to do it. It's a simple API that you can send your data in. We don't store the data in our system. You don't tell us anything about the data, what it is, because you just send samples, timestamps, and you get back results of the normal behavior and any anomalies discovered in it, and an image showing you the results. So if you really want to try it, just go to this website, go to this link, and try it. It's not open from our main website right now, so it's only for the people in this webinar. Just to mention, so I mentioned the large-scale system that we have. Our current Anodot customers, this is a partial list, are companies like Rubicon Project, Wix, Microsoft, Credit Karma, iView Digital, and more, AOL. And if you want to hear more information about Anodot, get a live demo, you can register from our website, and we'll be happy to contact back with you. So with that, I'm going to go back to Bill for our Q&A session.
Well, Ira, thanks for that excellent presentation. And we'll get started with today's Q&A session. And I want to thank the audience for their participation. And we've had a lot of questions that have come in during during your presentation, and we'll do our best to get through all of them in the time remaining. And during this session, I'll leave up this screen, which has contact information for Ira, if you'd like to contact him following today's event. So let's get started. Ira, that was very impressive. I must say that when I thought personally about anomaly detection, I thought much more narrowly about, for example, cybersecurity and intrusion and that sort of thing. And it's clear that Anodot is a very general purpose platform with wide applications. What would it take for a company to try and build one of these for themselves?
Oh, great question. So it's a hard question to answer exactly, but I can echo some of the things I've heard from both customers that we have and companies that have built it themselves. So for a basic anomaly detection system that will work on most of the metrics, and I'm talking about the stationary metrics, the standard techniques, the numbers I've heard range from a team of 6 to 12 people, with half of it being data scientists that know about time series data, and developers to build everything around it. Now, for building it at a large scale with a lot of different algorithms, it will probably take more than that. But I think the number that I've heard the most was around 12 people, expert developers and data scientists.
Well, I wouldn't be surprised. Thank you for that answer. And it wasn't entirely clear to me, but is the data science portion of this analysis automatically provided by Anodot, or do I have to have a data scientist that builds these algorithms within the Anodot platform?
No. So when we built Anodot, the main purpose was to provide anomaly detection for non-data scientists. So the idea is that it's not, so data scientists can be users of the system, but the idea is to have everything automated without having users configure algorithms or define algorithms or even know what is an algorithm. The idea is to provide a system that is intuitive, where the anomalies that we present are self-explanatory and easily understood by people who understand their business but don't care to understand data science.
Well, excellent. Thank you for that answer. Now, regarding the inputs to your system, can you speak for a minute about the types and formats and volumes of data that can be used as inputs, and what are the limitations that Anodot might have?
Right. So the inputs we take today for the two types. So most of the data that we're getting is time series metrics. So that means measuring something over time, and the data gets sent to us with a timestamp and a value and the name of what is being measured. That's basically all we need to know. Actually, in the taste of Anodot, we don't even ask for the name. Just timestamp, value, timestamp, value. So that's the input. Another type of input is events data. And by events, I mean more discrete events that you don't need to track over time, but rather could affect what you're seeing in the anomalies. For example, I did a deployment event. I deployed a new version of my application. That's an event. I started a marketing campaign. That's an event. It rained today in New York. That's an event for a company for a company like Uber or Lyft, because that affects the revenue. So these type of events can also be sent into Anodot, and our system correlates them with anomalies. And the way we do that could be a topic of another webinar later on. These are the two types. Now, in terms of limitations, there are so it's a scalable system. We have no limitation on volume. Today, we're at the number I showed you was good for last month. It's actually even higher now, and we keep seeing that growing. So really, there's no limitation on data volume.
Terrific. Thank you, Ira. Now, the audience would like to have some clarity around the issue of real-time. Now, we understand, of course, batch analysis, but when we're talking about real-time streaming within Anodot, can you probably just give some good examples? For example, you talked about card conversion rate. That would be one real-time time frame. But I presume that there are those that update much faster from machine sensors, for example.
Right, right. So yeah, so it really depends on both the business and the type of data. So for a lot of e-commerce businesses, again, some things you want to detect at minute-to-minute granularity, and some things you can live with hour-to-hour granularity. So card conversions are things that you want to know minute by minute. And as you mentioned, in a lot of the sensory data for machines, if you want to be proactive about not just proactive maintenance, but you want to detect that there is an issue, you need that again the minute-to-minute granularity at least. Now, in terms of the Anodot system, today we provide real-time up to a minute in terms of our system. We aggregate all the metrics to the 1-minute level, and once a sample arrives to our system, it takes up to a minute to send an alert that there is an anomaly in it. Now, this is the limitation if you go back to the previous question of the system today, but we haven't found many use cases where this is a real limitation. Reacting to anomalies within 1 minute is usually more than sufficient to all the things that we've seen.
Terrific. Well, thank you for that answer. And by the way, the audience is really engaged here and has cut right to the chase on economics. So let me ask this question on their behalf. How long does it take to show ROI on the investment in Anodot? Do you have some examples from your existing customers?
Yes, and we have some use cases also on the website that illustrate that as well. So actually you start getting ROI right when you start sending data. Let me give you a simple example actually from our case. When we started about 2.5 years ago, we had our first version out after about 4 months, and once we went live with it with our first alpha customers, it took about half a day for us to detect an anomaly in the metrics that we were measuring about ourselves. It was a very serious bug, but a very difficult to get bug. So we had metrics measuring latencies of a lot of parts of our pipeline, and one of the anomalies that popped up after really half a day was that every once in a while there was a spike in the latency for one of the steps in the pipeline, and it was every once in a while. It would have been very, very hard to detect otherwise without anomaly detection, and it was a bug that was really, there was some race conditions that was happening every once in a while, but if you're a large-scale system, every once in a while is too often. So that's an example from our case where we found something serious that would have been very difficult to find and even describe by customers because it was high latency every once in a while. And there are abundance of examples like that from on our website that can be read in the.
Yes, and each of those can obviously be very valuable to detect and correct. Yes. We've had a number of questions that have just come in. Again, about input to the system. So let me combine a couple of these. Does the input data need to be pre-processed? Is Anodot compatible with MapR versions of Hadoop for input? And could we even use something ad hoc like Tableau Viz data to input into Anodot?
So in principle, the answer to all the questions is yes. We have an API. We have a very simple API that to send data into, and of course in the MapR. And the question is the data organized as time series? So as I mentioned, our system takes in time series data. So if the data is organized as a time series data, then it can be sent as is. If it's in some text files and you need to parse them, then we don't parse these text files. We don't parse a raw log file that has a lot of text in it, but really there needs to be some parsing into time series signals. But anything that is time series, anything that is tabular, where one column may describe may have the values of what is being measured, and other columns are the properties of what is being measured, any type of data that is in that form can be injected easily into our system without any effort.
Okay. One of our audience members, I thought, had an interesting idea about a use for Anodot, and they asked whether or not Anodot was ever used in kind of an MDM role to detect data errors or mismatches when loading data into a data warehouse.
So the answer is yes. We have one customer that's actually exactly their use case, checking data integrity. So, of course, anomalies in the data that are being inputted into the data warehouse may indicate a real issue with the data, but as they mentioned, a lot of times it indicates data integrity issues. They get data from multiple sources, and then they process it and put it into their data warehouse. And oftentimes, the rules that they have for processing the data break because one of the providers of the data may change their format somewhat, or could be a lot of reasons for that. And then the anomalies basically indicate here is something strange in the data. They first check for data integrity issues. If there's no data integrity issues, then they check, okay, why is this anomaly happening? Does it affect the business in any way? And then move it to the other parts of the organization. But yeah, it's a very cool use case.
Yeah, that would be really interesting to try. So there are several questions here around the level of effort required to set up, but also around what metrics they should be examining. For example, if I had a lot of time series data and I just sent it all to you, how long does it take me as the client or you helping me to focus in on the metrics that are important?
Okay. So, in essence, let's talk about the learning part and then the part of what is important. So the learning part is done automatically as you start sending in the data. And what we often do with many of the customers, because, for example, if you want to detect seasonal pattern and you have a weekly seasonal pattern in some of your data, any algorithm would need a few examples of the season, like a few weeks, if it's a weekly seasonal pattern, to identify that. So we often inject historical samples first, and then go live into the real time, and then you get the value of the anomalies immediately. Now, what metrics to actually look at? There are two parts to this question. First of all, in our system, we have a notion of significance for anomalies, and I didn't discuss how we do it. We have another model for learning the abnormal behavior of the anomalies themselves and give them a score, a significance score. So any anomaly that we detect, you can easily see only the most significant ones in the UI, or be alerted on only the most significant ones, and those really highlight these are the most significant anomalies, and then if you want to go down and see less significant anomalies, mathematically speaking, you can see those as well. Another aspect of it in our system is to let you build both alerts and we call it anoboards, or anomaly dashboards, that focus on only a subset of the metrics that you're sent in. So oftentimes we see organizations could be sending 1 million metrics, but the users don't care about seeing anomalies in all these millions. So if I'm an analyst in charge of only part of the business in the U.S., I only care about anomalies that happen for metrics related to the U.S. So I can set up a dashboard of anomalies that will show me only anomalies for metrics in the U.S., and that helps a lot as well. So really, the one part is automatic, which is using the significance scoring that we provide for anomalies, and the second part is contextual, which is users set up in our UI anomaly dashboards, and it's really, really easy to set, that show them anomalies in the subset of the metrics that they care about. And this could be 100,000 metrics, but the dashboard will only show anomalies there that related to these 100,000 metrics.
Well, Ira, thank you so much. Those were great answers to some very good questions. And for those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Ira and the Anodot team so they can follow up with you after today's webinar. Now, I have just a few quick announcements. If you'd please mark your calendars for October 18th and our next DSC webinar, which is going to be sponsored by Alteryx, and that's entitled 10 Facts About the State of Analytics in Europe. Also, please remember, today's taping will be available for on-demand viewing later today, and you can find that on the homepage of datasciencecentral.com in the webinar tab located at the top of the page. Well, this brings today's webinar to a close, and I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to Anodot for their sponsorship, and our speaker today, Ira Cohen, for his insight into today's topic. My name is Bill Vorhies. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on October 18th. Have a great day.
Thank you.